Hi everyone, thanks for staying in this hot room to listen to my talk. It's very nice of you. So my name is Cristina. I work in the research team Embedded Security and Cryptography in Rennes, France, and this work is joint work with my colleagues Pierre-Alain Fouque and Benjamin Richard. I'm going to talk about this UMTS/LTE aka protocol. This protocol is a handshake protocol. It's an authenticated key agreement protocol, and we've seen already some of these in this session. So usually key agreement protocols take place between two parties, but in the context of 3G and 4G mobile networks, the idea is to use this kind of protocol in order to provide communication as a service, which is to say we want to provide service to clients, to mobile clients all over the globe, respecting their mobility thus, but also respecting their privacy. And obviously the focus will be on respecting their privacy in this talk. So the infrastructure in 3G and 4G networks features three types of parties, not just two. One of them is the client, so that's just the mobile phone. Usually mobile phones, they are associated with some operator, which is usually in their home country. So it would be Orange, maybe if you're in France. And then there's a third entity, which is not always trustworthy, which is called the server. So the server is the one who actually provides the service to the client, not the operator directly. So in the home network, the server and the operator are affiliated to the same network. Basically, they can trust each other a bit more. However, when people are roaming, and all of us do that on a regular basis, the client is served through some partner operator. So here in Germany, say Telekom, which has an agreement with the client's operator. Unfortunately, there is no guarantee of security in either the implementation or in, sort of legal aspects of the server. So there is no guarantee that the server is not subject to some eavesdropping or legal governmental eavesdropping agencies. There is no guarantee that this server has implemented the protocol securely. So what you want is to limit the damage that the bad server can do on the privacy of the client. So there's two concerns that we're really working on at the moment. It's the idea that we have to have a secure channel on which the service, something like messaging or minutes of talking, can be provided. On the other hand, we want the client privacy. So we want to prevent that so-called metadata can be used for tracing users or tracing their behavior, like what services they use more often. The AKA protocol is actually standardized by the third generation partnership project. Has been standardized about 15 years ago, and it has been maintained by the same group. It provides mutual authentication between the server and the client, and the key agreement, which allows to establish a secure channel. The main problem that we address in this paper is that the AKA protocol does not actually guarantee much of client privacy. And many people have come to tell me, yeah, sure, it's not a big problem because other layers of mobile communications don't guarantee privacy either. The obvious response to that is, sure, but if we're not addressing privacy at any layer, then we might as well give up on our privacy right now. So in this paper, we have analyzed some existing failures of this AKA protocol, and this is what I'm going to focus on in this talk. And then we also presented a fix for better security and privacy. I'm not going to present the details of our variant, just some higher level properties. And the main reason is that the AKA protocol is actually insanely complicated as it is. So the AKA protocol infrastructure features some secret and some public material. It's a symmetric key protocol, so the client and the operator have access to secret keys, the secret key of the client, the secret key of the operator, and something called a sequence number, which actually is used as some sort of randomness in a PRF. The client also is associated with some long-term and short-term identifiers. So the IMSI, IMSI, I will call it for short. The IMSI is the permanent identifier that each client is associated with. Obviously, the IMSI is unique per client. And then there are tuples made up of temporary information, which only the server and the client know. So these values are a temporary identifier, TMSI, and a local area identifier. So you can think of it like the zip code of the server, right? The tuple TMSI and LAI has to be unique. The protocol has 3 stages. The first one is user identification. I want to stress that in this part, there is no cryptographic authentication taking place. It's just for the server to know which client it needs to have material for. Then the second one is over a secure channel between the server and the operator, and the server is given some authentication vectors. And finally, the authentication vectors are used in a challenge response phase. So to understand how this works, the user identification phase actually has quite a bit of impact on the client privacy. And the idea is that once a client has been associated with a TMSI, that he never uses his permanent identifier again, which is to say, we're trying to prevent a client from being traced by leaking his permanent identifier. However, as we will see later, if the tuple TMSI LAI does not verify at the server is unable to associate the client with an IMSI and therefore has to ask the client for that IMSI. And this is something that we can exploit. Finally, if the server has an IMSI value, he can request from the operator of that client, and this is something that he will know once he knows the IMSI. He will request some authentication and key agreement material. So basically what happens, in order to skip a little over the details, the server does not have any of the secret keys that are shared between the client and the operator. So what the operator does is it basically it runs the authentication session for the server and provides him with all the necessary values. In red, the values in red are the confidentiality key, CK, the integrity key, so that's for authentication. IK, there's a masking key AK, and 2 MACs, one that identifies the server to the client and the other one the other way around. These 5 values are computed freshly for new randomness R and for new sequence numbers at each iteration of the protocol, and they are the results of 5 cryptographic functions. There are 2 algorithm suites that 3GPP has actually standardized. One is based on AES and it's called Millenage, and the other one is called Chuak, and it's based on Kechak, or the Kechak internal permutation. Once these authentication vectors including all the values on top are calculated, the operator sends these values to the server, and the server has enough material for n sessions. So going back to the actual authentication protocol, what happens is that the server first sends a tuple made up of one authentication vector, or one subset of information from an authentication vector, namely the randomness, a constant AMF, the masked sequence number that was used for the authentication, and a MAC that authenticates the server to the client. The client has to verify the validity of these information and afterwards recover the sequence number that was used. Now, the client stores its own sequence number, and it receives from the server the sequence number that was used by the operator for that session. These could be equal. I mean, in the best case, they will be equal. But if the 2 parties are desynchronized, they will be far apart. So what we want, or what 3GPP wanted, was that these values are not too far apart. If the values are too far apart and the MAC verifies, so we know that the operator is honestly desynchronized from the client, there's some sort of resynchronization procedure, which I will not cover the details of here, but which behaves differently than the authentication protocol. So finally, if everything checks out all right, then the client updates its sequence number to the sequence number it received, and it derives the session keys, sending with it also a response res, which is actually the MAC. So if everything goes all right, if all goes as planned, then there is a secure channel that is established with these keys CK and IK. Finally, in the final phase, there's a TMSI reallocation phase. Now, this is very important. The TMSI reallocation should be over the secure channel, so it should be encrypted and authenticated, but in fact, it is not authenticated. This is only encrypted. The result of the TMSI reallocation is obviously to give the client a new TMSI to use at the next session. So let's look at some privacy requirements. 3GPP said they needed 3 properties. First is a user identity confidentiality, the second is untraceability, and the third is location confidentiality. I'm actually using their terminology. It doesn't always overlap with the terminology we use in cryptography. So user identity confidentiality refers to the IMSI value, the permanent IMSI that should be confidential with respect to a passive adversary. Now, we thought that having a passive adversary today or nowadays is a bit under-ambitious. So we consider active adversaries as well. And we also want to ensure that the sequence numbers, which actually can be used to tell clients apart, should also remain confidential. Second one is user untraceability. That no adversary must know whether the same service is provided to a client many times. Now, this is basically in order to prevent adversaries from tracing your behavior. Now, we translated this into no adversary must know if some services and one particular service is delivered to the same client as before or not. As we discussed in our paper, basically this together with the unlinkability requirement that we had actually gives the untraceability in a much more modular way. So finally, there's a question of location. We want that the location of the client is confidential. That is to say, no adversary must detect the presence of a client in a given area. Now, because the adversary is in that area or possibly in that area, what we mean to say is that we don't want a correspondence between an IMSI and an LAI. We make no additional requirement to this. So we actually merge these 3 requirements into 2 more cryptographically defined requirements, provable key indistinguishability and client unlinkability. So let's look at some of the weaknesses of the protocol. Now, these are quite easy to follow, but I'll do it anyway. So there are 3 attacks that I want to focus on. The first one is the IMSI catcher attack presented by Strobel in 2007. Then there's bad TMSI and LAI management. And finally, it's the attack by Arapinis and al. Who linked failure messages and thus who can thus actually distinguish between clients. So IMSI catchers, they work very easily. The idea is to for the adversary to recover the permanent identifier, thus being able to track many users at many times. So the user if the user identifier IMSI is used immediately, then the adversary's job is done. However, even if we're using a tuple made up of TMSI and LAI, we just need to replace this tuple by a simple bit of randomness, and this will trigger the server to the backup procedure of requesting the permanent identifier. So again, the adversary has his job done for himself. Note that this is very parallelizable and extremely damaging as it reveals immediately where anybody is at any time and what they're doing. So to look at TMSI management and LAI management, well, the idea of this attack, it relies on a similar principle. Basically, if a TMSI and the LAI are not found by the server, then there is a permanent identity request. However, when we in order for this to happen, you need to have a valid TMSI, and the TMSI is sent in the reallocation message, which is not authenticated. So all the adversary has to do is to replace the reallocation message by some nonsense, which, because it's not a robust scheme, we actually can decrypt to some nonsense, and that nonsense is going to be used by the client again. So this is not as, this will immediately trigger again the IMSI leakage, and again is highly parallelizable again. Finally, there's a failure message linkability, which actually relies on on the fact that the adversary can manage messages in the network, finally, for example, it can stop an authentication challenge from reaching the client, thus essentially desynchronizing him, and then testing out which client will actually respond to this by means of a response, rather than by means of a failure message. Basically, to see this in perspective, this is not parallelizable. The idea is to make one client desynchronized and then targeting that client, seeing that it behaves anomalously with respect to others. To see our fix, I'm just going to say a few words about it, namely that we are actually reducing the 5-step protocol to a 3-step protocol. We're removing any type of resynchronization, and we're ensuring that the TMSI reallocation is well done. We have a fix that reduces the batch of authentication vectors to only one element. We're careful about how indices and sequence numbers are used, and we also encrypt the permanent identity and use an unforgeable identification procedure to prevent further attacks by active adversaries. Our results are, we actually achieve something that is weak client unlinkable, weak because we are not allowing any corruption of any clients, and which is key indistinguishable. Moreover, we prove that if we want to keep the structure of the protocol as it is, so without many modifications, then we actually can't get better privacy than this. So this is the best we can do. So finally, just to conclude,